Who wants to do label statements? 1, 2, 3, 4, 5, 6, 7. Right, label statements it is. Okay. This is really easy. It's like way down the list, right? It's like 13. You can whiz through this and be like, ah, it's brilliant. This is way better than GoTo. What does this guy know anyway? Who is this Alan character? We don't know him. So let me try and find the slides. It's number 14, or 13, sorry. It's way down here. There we go. Label statements. So labels are not new. Labels are old. But they're frowned on by some people who think GoTo is a curse, GoTo is a sin, don't use GoTo. And that's a real shame, because Swift has resurrected this thing, but with a new purpose. It exits scope. Because GoTo, of course, can go anywhere. Go to random places. GoTo fail if you write Apple's SSL code. And it causes issues, because GoTo is spaghetti code. Makes the code very messy. You can't follow the flow very easily. Swift has one purpose with these things, for exiting scope. That's all it's going to do. It can't jump somewhere random, it's exit the scope you want to exit. And it's particularly useful in inner loops and also complex conditions. So for example, this. Count from 1 to 10. Inside that, count from 1 to 10. Print out the coordinates. If we're at 25, break. No? Well, yeah. Break. How would you break out of that? Yeah, return the whole method. Just get out of the whole method. It's not that simple, I'm afraid. You can't do it. You've got to break, and you break out of this loop, but you're still in this loop. You carry on going around. You may end up with loads of things you're going to do, so you have to add a variable, you know. Are we really meant to exit? Equals true. Break. Check if that, and then break again.
HCF.
Check this out. Swift lets you say, outer loop, colon, for I am 1 to 10. And now, break outer loop. So it'll go from here to here. You cannot arbitrarily leap around. It just exits scope. So it causes a jump in your code, like GoTo, but it's better because you can't jump anywhere. It's not quantum leap. You can just exit the scope you're already in. So it's better.
Couldn't that have been solved with just using, like, breaking out these separate methods? So, like, this would just be...
Yeah, there's always ways around it if you really desperately want to. But let's face it, at some point you've got in a loop and you're like, how do I break out of this thing? It's not an uncommon place to be, let's face it. I'll walk through examples of this in practice, so you can see for yourself when and where it's useful. Preferences, displays, arrangement, mirror displays. Good. Scrap all this slow code. So if you imagine a grid of squares, and one of those squares has a treasure to be found by a brave adventurer. I'm going to show you one of my favorite constructors, my initializer, sorry, in Swift, which is the repeating count initializer. You could say this, you could say var board equals an array of strings. Two-dimensional array of strings. And it's made using repeating string array, repeating empty string, count 10, count 5. And that gives us a 10 by 5 multi-dimensional array of strings, mostly empty. If you haven't used it before, you can say things like string, repeating, Bob, count, 5. Let array equals that, do print array. There you go. So you can see Bob, 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 so it's repeating things. Anyway, so that gives us a 10 by 5 array of arrays, which is cool. So we can now say in there, somewhere, but of course we know where, is X marks the spot. That's where the treasure is. Can we find it? Let's find out. We'll do for row index cols in board dot enumerated. Then for col index col in cols dot enumerated. If col is X, then, oops daisy, then print found the treasure at row index col index, like that. So the treasure can only appear once on the board, as you can see, but this code is clearly wasteful. We've found the treasure, we don't want to carry on going round and round and round, so you might think, fine, I'll break out of it once I find the treasure. But again, that'll only break out of the inner loop. The outer loop will just carry on going round. So you're not really saving a great deal of work, saving a small fraction perhaps. Labeled statements let you name any loop or any if. And then you can use break or continue to exit intelligently. For example, you might say here, row loop, like that. And now you can write break row loop and exit out ahead of time. And that immediately gets out of both loops. You're saving all the rest of the work. As soon as it's found, get out immediately. And Swift takes us a step further, because you can exit conditions as well. So if you imagine a complicated bit of code, I'm not going to write all the functions for this because it's silly, but you'll get the idea. If we had if user requested printing, like that, then if the document was saved, then if user authenticated, then if we can connect to the network, like that, then if upload to printer, resignation.doc, then if print document, finally print successfully, TTFN. So that code goes through a series of checks, a safe series of checks. If then, if they're all true, finally, ta-ra suckers, I'm out of here, right? And that's fine. It's not uncommon. Yeah, come on, you never watched Tigger's big movie? Oh, it's called Tigger movie. Anyway, Tigger's movie. So, what we can do instead is write this. We can write printing, colon, if user requested print. Then, take all this down, like this. And instead, if not document saved, break printing. If not authenticated, break printing, break printing, break printing, break printing, like that. So the scope, the indents come way, way down. It's much clearer what you're trying to do, easier to read. And in fact, I would suggest, in this particular case, I really prefer to say what should be rather than what isn't. You would write instead, guard, 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 which forces you to break here. Validates you'll exit the whole scope.
So what's wrong? Oh, they're undefined.
Yeah, I haven't written these functions, but you know, it's example functions, right? You know, things doing things here. So it lets you write very, very clear code. That is all the same as that hideous tree of doom before the if statements, just simpler and smarter and easy to maintain. And that is labeled statements. Hooray for easy stuff, eh? Let's switch back to mirror displays. No, not mirror displays, the other one. And up here, label statements can go green. It's a victory. I'm hearing some mumbling at operator overloading. Sound good? Yes? Thumbs up? Okay, fine, all right. Let's do operator overloading. That is number 9. After lazy loadings, way back here. Closures, pattern matching, arrays and sets. Boom. This will test your history. Operator overloading. So operators are things like plus and minus and star and slash. They do things, right? And this particular thing, extending the operators we have so far and adding new ones, is, it's safe to say, loved and hated in equal measure. Some people love it, some abhor it. Python has no operator overloading. You see, we understand 5 plus 5. Even though you're in America now, everyone can do that. It's 10. We get that inherently. We learn that at school. And we can kind of reason my shopping list plus your shopping list equals our shopping list, right? We get that. But what would Henry VIII plus Anne Boleyn give you? History lesson. Pop quiz. Hot shot. What is Henry VIII plus Anne Boleyn? What's the result? Death. Well, also that. Yeah, that's true. An HBO series, I'm sure, isn't there? Is the result a married couple?
Sometimes.
Is the result a baby in the form of Queen Elizabeth? Is the result some sort of conjoined human with 4 arms and 4 legs? It's not immediately obvious anymore. The second one here, you can figure out our shopping list, easy enough. But this thing, what you actually get, you have to know ahead of time what it's going to mean. Now, if the result was a marriage, like it was in history, writing that is clearer. We can all see, even if you know nothing about English history, that creates a married couple. Easy. That's clearer. And it also hides complexity. 5 plus 5 is obviously simple. It's 10. Computers can do that very fast. But person plus person, well, does that mean arrange a marriage ceremony, get some flowers, find dress, get bridal favors? What could it actually mean? It could be all sorts of complexity. Plus, it can cause unexpected / hilarious results if you change the built-in operators. If you want to fox your friends, well, friends for now. So you can modify existing operators, or you can add new ones if you want to, your own custom operators to do things. But you do need to think about precedence and associativity. I'm going to walk you through what it looks like. So let's switch to screen mirroring again. Let's try this out. I want to start again, simple, 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 basic, 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 and work up from there. That's how I think you learn effectively. So we'll do something like this. If 4 is equal to 4, print match. Else print no match. Now, hopefully, we can all agree that's going to print match. Easy enough. But with operator overloading, it doesn't need to anymore. We could say something like this. Func equals LHS int RHS int returns a bool. Return false. No matter what, it doesn't match. Now it's printing no match. You just put that in a really obscure file in your Swift project, and that's it. April the 1st will never be the same again. It will fox your friends for a good old time, that one. Even better, what you can do is you can do something like if arc4 random uniform 1 to 10, so it's occasionally wrong, but mostly right. That was even worse, because you can't track it down. It was really good. It sounds awful, but there you go. And you can screw your friends up, and you can do anything you want to, because for Swift's like, yeah, fine, fill your boots. If you want to change that, you can change that. Cool. So again, I said before, there's PEMDAS in the US, parentheses, exponents, multiplication, division, addition, subtraction. That's the precedence order. When you look at numbers being added and subtractive, that's the precedence order you have, as well as association. So let's look at precedence. Let's say, I'll comment this out so you can do your brains a little bit. Let I equals 5 times 10 plus 1. What does it equal? 60. 16. Brave. 51. 51. Because it's evaluated as this. That's how Swift sees it.
Well, that's wrong.
No, it's right.
Yeah.
Now I'm seeing why I think GoTo is wrong. See, you're wrong about a number of things.
The
Swift's,
languages must be wrong.
yeah, so yeah, the whole damn maths world's wrong. I'm right. It's 16. So that's how it sees it. Swift follows the basic PEMDAS rules like everybody else does. We all agree with this apart from that guy. And
Wait, what? Times has a higher precedence,
yeah, it does.
so it's executed
First.
Oh, you're right. Sorry.
Use some coffee, man.
Yeah, you need coffee.
So it runs it in that order. It sees it as that. That's what it's designed to do. And what we can do is we can look at the way Swift handles this, and they're all declared. You can actually just dig around in Swift and find out how it declares its stuff. And what you'll see is lots of code like this. You'll see precedence group, addition precedence, precedence, there we go. And then associate to the left, activity, left. And it'll have a higher than is range formation precedence in Swift, which means addition's higher than that. And you see another one called precedence group, multiplication precedence, associativity, left, and then higher than addition precedence. So someone's gone through to Swift and added all these precedence levels in and ranked them all higher than. And so you know exactly the flow going down of exactly highest down to lowest, which is how maths works. They then go ahead and they define the operators themselves. They say things like infix operator star. Star should be given multiplication precedence. No worries. And infix operator plus addition precedence. And the same for minus, because they're the same precedence. So it declares these precedence groups here, like that. Tells them where they associate, left or right. Says where they rank in the grand scheme of things. And I can go ahead and assign it. I can say star is infix between two operands. And it's in that precedence group. Plus in that one, minus in that one. And you can actually monkey around with this if you choose to. You can say, actually, I want to take, let's do hideous, like star is range formation precedence. We can push it down the precedence levels. And now we're getting 55. So I'll undo it. 51, redo it, 55. Because now it's reading that. It's been pushed down the stack, so addition comes first. So it'll do 10 plus 1, make 11 times 5. So you can really monkey around with the built-in operator if you choose to, and screw things up. So you'll also see the associativity is important as well. So you can see here, we're saying, oops, up here, we're saying that addition precedence goes to the left, which matters. If you had something like this, let I equals 10 minus 5 minus 1, what will that be, do we think? What will that add up to? 22. It's hard to get 22 out of that. So it binds to the left, so it'll be read as that. 10 to the away 5, 5, 10 to the away 1, 4. If we'd said, actually, stick to the right side, it's now going to run 5 minus 1, 4, 10 minus 4, 6. So you can fiddle around with the built-in operators if you choose to. Now all this is important, of course, because these same tools are used for your own operators. We can write our own one. And we can actually, oh, sorry.
Yeah, so how does that actually work? Is it, I would assume all this stuff is like defined already. Is it just replacing?
Mm-hmm, yeah.
Yeah, okay.
It's just, that is literally the code from Swift's own code.
Yeah.
It's just all Swift. It's all written in Swift. Large chunks of Swift are written in Swift.
So it's just like totally fine to like redefine.
No, it's alien, horrible, don't do it.
Well, I mean, that's not what I mean. That's not what I mean. Like something that's already defined being redefined.
Yeah, it's fine. You saw it there. Yeah, totally fine. I wouldn't do it, but it's totally fine. But the thing is, I'm showing you these things not because I want you to jape your friends, but because those same things are used for your own operators. So precedence group and index operator. We're now going to use them to have your own operator. And we're going to start off by extending an existing operator. We're going to extend star, multiplication. We want to write code like this. Let result equals 1, 2, 3, multiplied by 1, 2, 3. So it wants to return, shortly, 1, 4, 9. 1 times 1, 2 times 2, 3 times 3. Doesn't work. You can't multiply arrays in Swift. Yet. We can go up here, we can add our own multiplication function. We can say func star, where the left-hand side is an int array, and the right-hand side is an int array. And it will return an int array. We'll kick off with a guard. We'll say guard LHS count is the same as RHS count, else return LHS. So if they are not the same size arrays, don't try and get stuck into this because you'll have problems with indexing and so forth. Return HS. That. Then we'll create a new result array, int array, and loop over it for index int in LHS dot enumerated result dot append int times RHS index. So I go through each item, pulling out its position and its value, and multiply its value against the position, the equivalent value in the right-hand side array, RHS index. Then return result. 1, 4, 9. So that operator already exists. It's been defined, how it associates, what its precedence group is, whether it's infix, postfix, or prefix, already done for us. We're hooking into that and extending it to support int arrays. As you can see, it's very easy to do. So, you can also add new operators. For example, we're going to add one for star star. Yeah. To make exponents, to make things go powers, raising one thing to a power of another. And this is actually very easy to do. We use a built-in function for this. So let's scrap that code. We're going to say infix operator star star. This is a new operator, star star. And what we want to do is add a function for it. Now I'm not going to just give it a precedence group or associativity. I'm going to use the defaults. It's fine in this particular case. You can add it your own later on if you want to. I'm going to write func star star, LHS double, RHS double, returns double. Inside there I'll use pow, which is built into Foundation, LHS, RHS. Pow, pow. And now I can say, let result equals 2, star star, 4. 16. Great. 2 times 2 times 2 times 2. That works fine. But this will not work. 4 star star 3 star star 2. Not going to happen. And in fact, even this won't work if we had 2 times 3 plus 2. Meh.
It doesn't know associativity and precedence.
Exactly. We have to tell it where star star ranks in the grand scheme of precedence things. So we can create a new one. We can say up here, precedence group, exponentiation precedence. Exponentiation precedence. There we go. I'm going to say this is higher than multiplication precedence. This is going right up there. And associates activity to the right. In fact, there's a colon here. Like that. To the right. And now infix operator star star should be exponentiation precedence. Exponentiation precedence. There we go. Boom. So it now knows where it fits in. So it will correctly say that's 10. 2 times 2 times 2 plus 2. So it fits in correctly to the grand scheme of things. So it's very easy to do. You can also modify existing operators to do interesting things. So I'm going to modify the ... operator, which is the closed range operator. I'm going to make it do this. Let range equals 1 ... 10 ... 1. So it'll go 1 to 10, back down to 1 again, which you can't do right now. Doesn't know what to do. So it'll contain 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9, 7, 6, 5, 4, 3, 2, 1. And this function needs to do two things. It has to calculate the new range by going from the right-hand integer, here, up to the highest point in this range, which is 10. Then reversing it. It does it that way because you can't create descending ranges in Swift. Ranges must only be ascending. So it creates a ascending range and reverses it to create a descending range. Then it appends that to the existing downward range and returns that as a result of the function. So we can say this. Func ... LHS. Now this thing technically is called a countable closed range of ints. That's Swift's name for it. On the right hand side is a plain old int, 1. And it's going to return an int array. So first it calculates the new range. So it'll do let downwards equals RHS up to, excluding, LHS dot upper bound reversed. So again, ranges must be ascending in Swift. You can't have descending ranges in Swift. It doesn't work. And it's whinging slightly for some obscure reason. We'll find out shortly, I'm sure. Why are you whinging? Why are you whinging? Back in a second. And then we're going to return that back to the call site. So we'll do return array LHS plus downwards. There we go.
Why upper bound?
Well, that's the highest number. So 1 and 10, 10 is the upper bound.
Oh, yeah.
So this will count from 1 up to it's leaving 10. The reverse it counts from 9 down to 1 again, because you can't go from 9 to 1 otherwise. Then returns it as an array of the previous thing, 1 to 10, plus downwards, the new thing. It doesn't work yet, because you can see it's complaining. It doesn't know whether to read that as, as 1 to 10, or as 1 to that. It doesn't know. It can see there's two options here, so it kind of hedges its bet a little bit and gets it wrong. So you got to tell it what to do. So we'd write something like this: infix operator, ... range formation precedence. That's what it is right now. That's what it currently has in the Swift code. And it also has a precedence group. Precedence group, range formation precedence. And it'll say higher than casting precedence. This is Swift's own code. So that's what it is right now, and that kind of works. The problem is, that Swift's code, you can see there is no associativity in there. It doesn't know whether to bind to the left or to the right. We have to try and tell it that. So we can write in here, associativity, left. Give it the information it needs to make it work. Now you can see it working. Counts up, counts down for a single range. And that's operator overloading. So there are options here, making new ones by yourself, fiddling on existing ones, customizing existing ones, futzing with it to do interesting things like that.
So you could easily do implement downward range.
You can't do downward ranges in Swift.
To find an operator to do it, no?
But the operator would do it, but it would crash when you try and do it.
Why?
You can't have downward ranges in Swift.
You just made one.
No, I didn't.
You reversed one.
It's just an array.
It's an array of integers.
Oh, it's not a range, it's an array.
Correct. You cannot have descending ranges in Swift.
So you can make a downward array operator.
Yeah, which is what we're doing here, basically. Yeah. The thing is, ranges are usually for loops and stuff and enumerating over them. The difference is nil. That's fine. That's fine.
Why aren't you getting an operator?
Arrays and sets?
Sure.
Well, it's only you have a 50% chance of getting what you don't want here. Let's face it. At this point, it's pretty easy to satisfy everybody, I hope, because it's all there. All right, arrays and sets it is. That is number 7. Let's try and find number 7. Number 7, number 7, number 7. OOP. Pop. Pattern matching. Closures. There we go, arrays and sets. Nice and easy, this one. Arrays and sets. So arrays are obviously an epic workhorse of Swift. They're used in lots and lots of places. You use them all the time, that's great. And they are completely type safe in Swift, which is also good. They are vaguely type safe in Objective-C, but only vaguely. And they work great when your data conforms to comparable. There's another kind of array which most folks aren't aware of. It's a shame. And it's called contiguous array, which is faster and used extensively in Swift's standard library. There are also sets, which are, of course, fast and flexible. And I'll walk you through arrays, contiguous arrays, and sets, just quickly. So, let's have a look. Let's go back to mirroring displays. Cool. So, arrays. Easy enough. We can say var names equals, let's do array Taylor, Timothy, Tyler, Thomas, Tobias, and Tabitha. Then let numbers equals 5, 3, 1, 9, 5, 2, 7, 8. 2 arrays of stuff. Fair enough. We could say let sorted equals name.sorted. And we understand intuitively what that's going to do. We'll get back an array of names, Tabitha, Taylor, sorted like that across the way. Thomas, Timothy, Tobias, Tyler. And if you want to write your own sorting function, you can do. It's worth doing it at least once. You can see exactly how it works. You could say names.sort, open closure, and write it yourself. Not terribly hard. You could say print comparing $0 and $1. So you can see what it's doing behind the scenes. And we're going to do it so that Taylor, clearly being a superior singer, will always come first. So we'll write if $0 is Taylor, we'll write return true. Else if $1 is Taylor, we'll return false. Else regular sort. Return $0 is less than $1. So sorting using custom code, and you'll see it whizzes through. Timothy and Tyler, Tyler and Timothy, Thomas and Tyler. You can see exactly what it's doing. It sorts and sorts and sorts until it finds the final result. And you can look at the names array now. You see Taylor has been sorted to the front, even though lexicographically she has no place being there. So you can create your own sort if you really want to. I do recommend you try it at least once because it lets you see how sort works, or how max works, or how reduce works. You can see exactly what it's up to, which is great. Now, adopting comparable we saw already, if you remember. We did comparable earlier, I think, with functional programming, I think, perhaps? Don't know, it was a while ago. No, I think it's about functional programming. I think we did comparable for our person structure, something like that, didn't we? And you can add it here if you want to. It's better than having sort by that like itself. But relying on the built-in is usually good enough, because for this case, you know, Tabitha comes first, then Taylor, and so forth. The built-in alphabetical sort makes a lot of sense. Same for numbers. You can do, you know, let sorted equals numbers.sort, and it will sort just the logical, obvious way we expect numbers to be sorted. 1 will come first, then 2, then 3, and so forth. Easy. You can also use min and max to find the lowest and highest values. Remember, this is optional because there might be no values in there. And of course, for names, min and max will return whichever string comes first after sorting, or last after sorting in case of max. So Tyler is the last after sorting string. So in this particular case, it's actually more efficient to use max if you want to find that value. It doesn't have to keep on sorting. It just whizzes through it once without moving it again and again and again. So it's faster. Anyway, we've already done conforming to comparable, if you remember. I showed it to you before. I can show it again if you want, but I don't think there's any point. But you can, of course, add and remove items to arrays by doing things like, let's make a class first. Let class dog var, hello, extra brace, var name string, var breed string, var age int. In fact, forget the name, pointless. There we go. I can do let Poppy equals dog. Let's make an initializer this quickly. Init breed string age int self.breed equals breed self.age equals age, and now I can say dog, there we go, breed poodle age 5. Copy and paste 2 times. Let's do let Rusty and let Rover. There we go, that's good enough. So Rusty is going to be a Labrador age 2, and you're going to be a Corgi age 11, and we can say let dogs equals Poppy, Rusty, Rover. Brilliant. Okay. So far, so good. To add a new one, you can say, just, let Beethoven equals dog, breed St. Bernard or Bernard, age 8, and then dogs plus equals Beethoven, like that. Because you can append one array to another. I've made that constant. There we go. You can append one array to another. Plus equals is overloaded to handle that. So what I have to do is put Beethoven in an array by itself and append it. Or you can do append by itself. You can also, remember, I showed you before, use pop last to remove items. But it's optional. So if I do something like if let last dog equals dogs.pop last, then just do stuff with last dog here. And I'll remove the final dog and send it back to you to work with. But it's optional, because there might be no items in there, so I'll wrap it carefully. Just quickly, there are a few more things you can do with these things. It's common to see people write code like this. If dogs.count is 0, then meh. It's actually more efficient to write if dogs.is empty. That's a good idea. And you can also use the reserve capacity method. Dogs.reserve capacity. How much space do you think you need? And this is helpful. Now, I'm not write code for you here, but you can benchmark it later. It is significantly faster to be right about reserve capacity than not. So you'll see in all Apple's own code internally, always reserve capacity. But it's not a free operation. It's not a free operation. It won't be like, oh, our space is 50 and you want 100, I'll just make it slightly bigger. It will copy it to a new space in RAM with enough for 100 and make sure they all line up neatly. So if you do it after you've made your data, you have to recreate it all. It's a big burn in your data. It's completely pointless. There are also contiguous arrays. So we can say something like this.
So, sorry, reserve capacity, well, let's say you say it's 50 items, and then you add more items, what would happen?
It's fine. It'll work. It's a minimum.
It's the minimum.
Yeah.
What
So for example, remember I showed you before,
what if you had less than 50? It won't.
it doesn't take up the space. Yeah, it's prepared to do it. Yeah, it's prepared to do it. It's just an optimization. It keeps it nicely in line. It makes things faster. You know, if you ever have to go over an array and modify it and you've got a return array you're adding to, first thing you do, reserve capacity. Enough for, I think I'm going to have to return, pass it back before you add anything. Otherwise it has to copy it across and it's extra work. So Swift has two kinds of array. You normally use regular arrays. There are also contiguous arrays. You can say let array 1 equals int array, like that. Which is syntactic sugar, of course, for let array 2 equals array int, like that. That's the same thing. But you can also create contiguous arrays. You can say, let array 3 equals contiguous array int. And they're slightly different. Now they have all the same things you care about, like min and max and map and stuff. It's a monad, it's a funct, all that kind of thing. Things we understand and know. But they guarantees to store your things exactly next to each other in RAM. There's no sort of scattershot all around the place, which is what you get with fragmentation. So they're faster. And Apple's documentation says, use this when you want C-like performance. You want the thing to go as fast as possible. And it does say, it claims to say, that the performance is identical when you use non-class types. Apple says. So if you're using structs, for example, if you're using an array of ints, Apple say officially is as fast as an array of a contiguous array of ints, according to Apple. In practice, they're wrong. But
Claim that array of int is the same performance as contiguous array of int.
yes, that's what they claim. They're wrong. They claim that.
All right.
Now, the reason they say that is because there's a lot of magic in Swift around bridging between things, between arrays and NS array, dictionary, NS dictionary, and da-da-da-da-da. And when you have a class type in here, say, UI view, that can no longer be a native Swift array. It has to bridge to NS array now to store these things. Now, in practice, I can promise you, contiguous array is significantly faster across the board. No matter what you do, it's just faster.
Contiguous.
Yes, always faster. So the Swift compiler can be clever. It can say, well, it's an array of integer. I don't need the extra work here. It's faster, but it's just faster across the board. Every time this is faster. So if you can, use it. And again, if you read Apple's own code, standard library, you'll see contiguous array across the board. What they'll normally do is they'll have, func do stuff with items string. They'll have a function like that, right? And they'll say var result equals contiguous array string, then result dot reserve capacity, whatever it is, probably items dot count, usually something like that. Then lots of work here. Then return array result. So you get back a regular array like you expected, but all the work they've done in between is fully optimized and fast. And it's a common paradigm. I might even try and show you. Let's find out. Shot in the dark. Yeah, there you go. So you can see a lot of places. It's Apple's preferred way, for a reason. Anyway, so give it a try. And there's sets, of course. Sets are very helpful. Sets are like arrays, that they only contain unique items. You can't have more than one at a time in there. This makes them significantly faster for doing things like contains. If you do contains on a array, it is big O-O-N, O-N, meaning it'll take as long as you have items in your array. So go through each one. Is it you? 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 No, back. So worst case is it takes as long as you have items you have. Whereas with a set, it is O1. It runs in constant time. It knows very quickly. These are extremely optimized data structures. I remember going to a talk at DubDub 13, 12, and they were trying to explain how NSSet works and why it's so clever. And saying basically we have a hashing algorithm that comes in, calculates a hash, puts it in a bucket for all your items. And if we find the buckets are uneven, if it's like 20 here and 2 here, we will change hashing algorithm and rehash to make it equal. So they've got a lot of work in here to make their set hashing very, very fast and very efficient to find your items. So it's guaranteed to be extremely fast. And you can create them easily. You can say this, var set1 equals set int, and give it an array, 1, 2, 3, 4, 5. That's it. Now look at the output, 5, 2, 3, 1, 4. Thanks. Because they haven't got an order, these things. They just work how they feel like, and we don't really care normally. You don't have to worry about it. You also create them from ranges. You can say, I want to make a set from 1 up to 100. There we go. in their own little merry order. Or you could do set1 dot insert 6 or 105. Add them by hand.
Sets don't have, they can't have duplicated values, right?
I'm sorry?
Sets don't-
Duplicated values? No, they can't. No, they're all unique. I did almost type there append, which is wrong. It's insert, because you don't append, there is no order. It's insert into the set. And of course, you can use contains. So you can say if set1 dot contains 105. And it's extraordinarily fast. If you can, you use sets for your contains work. Now, the handy thing about Swift is you can convert between arrays and sets very easily. You can say var set1 equals set int. I'll give it 1, 2, 3, 4, 5, like that. Then var array1 equals array set1. And var set2 equals set array1. You just bounce between them. You notice there's like braces and brackets here. One braces means sets and one brackets means arrays. You can bounce between them very, very quickly. And of course, you can loop over them. You can say, for item in set1, print item, like a regular thing. You can even sort them. But notice, when it's sorted, you get back an array of integers. That's the way you sort sets. You can't keep them otherwise sorted. They come back as sorted sets. Arrays, sorry. There are loads of extremely fast and optimized set operations you want to think about. So we could do things here. We could say let spaceships1 equals a set. And in here, I'm going to add some spaceships. I'm going to add Serenity, Nostromo, and Enterprise. Then also, let spaceships2 equals set. I'm going to add here Voyager, Serenity, and Executor. Like that. You can union them. Equals spaceships1 dot union spaceships2. Again, sets don't contain duplicate values, so you'll see every ship appears only once. Executor, Enterprise, Serenity, Voyager, Nostromo. So there's no duplicate Serenities in there. Doesn't happen, doesn't work. There are also intersections. You can say spaceship 1 intersection spaceship 2. Where's my mouse cursor gone again? There it is. Intersection spaceships 2. So this returns a new set containing only elements that exist in both sets. In this case, it's Serenity. That's the only one that appears in both places. There's also the unhelpfully named
Is that a set or an array that it returns?
a set. Should be, I believe.
Looks like it has the.
Yeah, it's a set. Intersection. What was I typing? Sorry. There we go. There's also one called symmetric difference, like that. This returns only the elements that don't exist in both. So it's like exclusive. Now they all have in-place varieties and they're called form. So you could use things like form union, form intersection, form symmetric difference. They're scrubbed out because it's a constant, it's not going to work. But that means do it in place rather than returning a value. And there are loads of other things you can do. You can have subsets and supersets and so forth. You could say, what do I have so far? Serenity, Nostromo, Enterprise, good. Void, Serenity, Executor, good. And add another one here. Let spaceships 3 equals set, Galactica, Sulaco, and Minbari. I watch a lot of TV. Probably too much TV. And then what we can do is we can say to here, let spaceships 1 and 2 equals spaceships 1 dot union spaceships 2. So we've got 4 sets in total. 3 individual plus 1 that combines the 2 together. And now we can start using subsets and supersets. We could say spaceships 1 dot is subset of spaceships 1 and 2. So a subset is a set that contains only items that exist in the other set. So in this case, spaceships 1 does contain only ships seen in 1 and 2, unsurprisingly, because one's made from a superset of the other one. We could say spaceships 1 dot is subset of spaceships 1. The answer is also true. spaceships 1 dot is subset of spaceships 2. The answer here is going to be false, because they're different ships. There's also spaceships 1 dot is strict subset, which is different. And I can say spaceships 1 and 2. The answer is true. But if I did spaceships 1 dot is strict subset of spaceships 1, it was true here for a regular subset. Now it's false. So what it's going to say is it's false because, yes, they contain the same ships, but that's not enough. It's got to contain the same things, but less than the other one. It can't be the same when it's a strict subset, because subset implies, smaller than. So strictly speaking, it's not a subset. If you're cool with it, a subset, it can be the same. It's okay. Plus, there are superset varieties. You could say things like spaceships 1 and 2 dot is superset of, and give it a set. So you can do spaceships 2, which is true. But spaceships 3 is, of course, false. Doesn't involve that at all. There's also a strict version of that as well. Strict superset of spaceships 1. The answer is true, because it contains all the items of that, plus some more that weren't in there. There's even a disjoint version. You can say spaceships 1 dot is disjoint with spaceships 2. So there's loads of operations here in sets. And of course, there's also NS counted set, which you've seen already. So I'm not going to do it again. And that is sets. Is there one thing left? That's not bad. That's pretty going. What was it? Oh, tuples. Yeah, tuples wasn't one of my favourites, but there you go. We left it to last. Stuck with it. Tuples. Time is it? Oh, it's 5 o'clock. I think we're basically okay here for a while until they boot us out, I guess. Right. So let's colour in that. Tuples is... Oh, I colored the wrong one, sorry. It's number 10. Number 10. It's way... Arrays and sets after that. Operator overloading after that. Tuples. Cool. Okay, so tuples are often thought, I think, in terms of simplified anonymous structs. That's how people think of them, I think. Simple ways of just throwing data together and spitting it out. So I can't be bothered to make a struct. But that isn't quite true. In fact, that isn't remotely true. It's more complicated than that, naturally. Because in Swift, they're used almost everywhere. They are literally the most pervasive part of Swift. If you thought closures or lazy loading were pervasive, you ain't seen nothing yet. Tuples are literally everywhere in Swift. So, func do nothing, let result equals do nothing. What is result? What data type is result?
An empty set? Nil?
Nope. It's void, but void is an empty tuple in Swift. It's explicitly defined as an empty tuple. Yeah. Plus, this code's fine. Int tuple 1, it's fine. It is fine. Every type, integers and strings and so on, is effectively a single element tuple of itself in Swift. Yeah. It really is. Assigning an integer to a single element tuple like that is perfectly fine, and vice versa. Both are exactly the same thing. Apple docs explicitly say if there is only one element inside the parentheses, the type of a tuple is simply the type of that element. It's the same thing.
Is that true in Haskell as well?
I'm not sure. They are literally the same thing. So you can even write this, value 42, and that's fine. So when Swift compiles the first line, it will ignore the label. and make it a single element tuple containing an integer, which is in turn identical to an integer. Now, in practice, this means you can't add labels to single element tuples. It won't allow you to do it. If you try and force a type, you will get an error. You're trying to force Swift into a corner and it doesn't understand what to do. It will bail out very quickly. So they are everywhere. I mean absolutely everywhere. If you return nothing from a function, you get a tuple. If you return several values, you've got a tuple. If you return a single value, you also get a tuple, right? You can't avoid these things. So I think it's fair to say you are all frequent tuple users, whether you like it or not. You are already tuple experts. But they can't have methods. So when someone thinks, oh, they are simplified structs, they really are quite simplified. They cannot have methods attached to them, and they cannot conform to protocols. So you can't have, comparable or so forth. Doesn't work. Not allowed. If you do happen to want that, I've got just the code for you. You're looking for a struct, right? At some point, you've got to give in and go for a struct. So that is tuples. I'm going to try and walk you through some examples so you can sort of see it working in action, because they are quite beautiful things. All right, mirror displays. Scrap all this junk. Okay, so we're going to say var Singer equals Taylor Swift. Okay, very simple tuple. That has a type. It might look like a dumping ground for data, but it's not. That has a type. It's a string. You can't redefine that to be Singer equals Taylor and then Swift and then 26. Because the type is string, not string int. It's not a dumping ground. It has a real type with type inference just like everything else. If you don't have names like we have here, of course you can use numbers to access things. You can say print Singer.0 to read Taylor, or Singer.1 to read Swift. But broadly speaking, you want to have names. It's much easier. You can use name Taylor, or first even, sorry. First is probably better, isn't it? And then last Swift. You can say something like first. Bit nicer. If you do have tuples within tuples, which is not uncommon but not really recommended, you have to use 0.0 to index further and further into things, which is not very pleasant. So you'd have something like this. You'd have first Taylor, last Swift, then address. I don't know where she lives. She lives at 555 Taylor Swift Avenue, obviously, in... no, this isn't real. Nashville. Right? And if I'll read that out, you got to do like print Singer.2.2, which is just grim. You don't really want to go down that direction. It's much nicer to say address.city or something like that to give them all names along the way. Much nicer. This is built-in behavior, but doesn't mean you should. So do give your things names, a better idea. And these names actually form part of the type. So if I had first Taylor, last Swift, I cannot now say Singer equals first Justin, fish, trout. Not allowed. Because they form part of the type.
But you can't say last something, first something.
Yeah. You can, as long as the names are the same, you're okay. But you can't screw it up.
But they don't have to be in order, right? The same order.
Do they not?
Do they or don't they?
Not liking it.
Well, then what
Oh,
is
it works. There, it worked.
Huh?
It'll work. I haven't tried that before. That's
Then
interesting.
What does .0 refer to?
Yeah, it's very interesting. I don't know why they'd allow that. I would never do that because I'm not crazy. But
Yeah.
oh Lord, that's awful.
Ha ha. Interesting.
Don't do that.
All right.
I might find a bug on that. That's hideous. Don't do that. I'm not going to delete that. We can cut that from the recording later, can't we, Evan? Don't allow people to do that. It's hideous. I'm even sure that's possible.
It's not with a trout.
Yeah. You can give these things closures if you choose to, but a closure is not the same as a method in this particular case. I'll show you why. If we had a Singer and we had first Taylor and last Swift then had a closure inside here called sing, we might have like, you know, lyrics string in, some lyrics you sing, and I'm going to make this thing just print, let's do lyrics like that, it's fine. So there's a closure inside the singer thing. We could write singer.sing, haters gonna hate. And it kind of looks like a method, right? It's not, but it kind of looks like it. You know, we couldn't say this. Taylor, oh sorry, first says lyrics. You can't read the first name value of your tuple, which you will be able to do in a struct or a class, because it's a real method, it can handle that. This thing does not understand it's part of something that has a first value, it can't read it. So you probably don't want to do that, let's face it. Tuples are most commonly used, I think, for returning multiple values from functions. That's one of the big leaps forward with Swift, is finally you can do decent return values.
So once again, the interop question comes up. It appears to me
What does
so
it do?
far
Yeah.
that Objective-C does not know
No,
what to do with it.
no, wouldn't know what to do. I don't know what it does.
It's too bad.
You know, yeah, it is too bad. So, for example, mostly I don't care. Mostly I'm like,
Well, I have a lot of Objective-C.
yeah, I know, exactly, good luck to you. Mostly I'm like, well, come on, suckers, get with the game. What year is this?
So what?
What year is this? Mostly I generally don't
I
care.
have a lot of Objective-C. The
I-
project to eliminate it is going to be going on for quite a long time.
Yeah. Yeah, my last project was 110,000 lines of Objective-C,
Uh,
which was a real joy to maintain. And it'll never be written in Swift. It'll never happen. The company will never go. Because the problem is, you write it in Swift and it looks the same, works the same, it's probably buggier now. You know, no one's going to go, yeah, that sounds great, let's spend £1 million doing that, or $1 million doing that. You just wouldn't do it. So I think a lot of code will stay Objective-C. But the problem is that some of the more advanced features of Swift you just do not get. For example, protocol extensions don't exist in Objective-C. So if you have, for example, if you extend UI table view data source to always return 10 rows something, that will not be visible to Objective-C. And in fact, if you mark it, if you use @obj_c for your protocol, that's also invisible to Swift. Swift can't use it anymore, can't be a protocol extension, because it's a wrong kind of thing, it won't work anymore. Never the twain will meet.
But class extensions are very handy.
Yeah, that's allowed,
Yeah.
but not protocol extensions. So it's possible that maybe, you know, Apple have worked very hard since Swift to make Objective-C better. The nullability macros were very helpful. The lightweight generics were very helpful. So they are slowly making Objective-C better and more like Swift, but I suspect they're only doing it specifically to aid interop,
Oh, shit.
to make their own APIs nicer and make other APIs nicer. So it's possible they might say, this would be great to go the other way, but doubt it.
Right. I mean, I wouldn't be writing any new code in Objective-C anymore, so.
Good.
what's the point?
Glad to hear it. Yeah, what is the point? You're right. So returning multiple values is great because you can return as many as you like, and they have nice names. It's very clean and lovely. If you had something like, you know, func fetch weather, this thing will return a weather type, then cloud cover as an int, then high, of course in degrees Celsius, because this is a real world, not Fahrenheit. Who uses Fahrenheit? Pff, low int, and then something like, you know, return sunny 50, 32, 26, whatever, like that. And you can say let weather equals fetch weather, and do weather dot cloud cover, and read it back, which is great. It's very nice. Now you can also do destructuring. It is very popular in some languages like ES6. You can assign variables immediately. So you could have said this. Let type cloud high low. And now we can say print cloud directly. So it pulls apart the tuple when it's returned and puts them into individual variables or constants for you, which is fine. Now if Swift didn't have tuples, there are a number of ways of doing this. I've used, I think, all of them, and I hate all of them. This would have to work something hideous. You have to say it's going to return an array of any, not in caps, like that, and then return individually items like that. Then, worst of all, let weather equals fetch weather. Do hideous typecasting. Let weather type equals weather 0 as string. You know, junk like this. It's really quite ugly. And yet this is precisely how functions often work in Objective-C, because you haven't got a choice. So that's very common, just sad. And
Dictionary.
oh yeah, dictionaries, yeah, it's also possible, yeah. But still, the typecasting is appalling. Whereas no type safety is there, let's face it. There's no type safety whatsoever. It's all stringly typed, which is just hideous. Or worse, even worse is, if you see someone write this kind of code, type in out string, like that, and then cloud cover in out string. And they just rewrite in place, you know, let's say, you know, type equals sunny, like that. And that is just hideous. So don't do that, please. Tuple's much nicer.
Oh, this is the same as that passing a double star thing into an Objective-C function to get another return value out of it.
Yes, exactly that. Yes, exactly that. Yeah. Which you see is not uncommon in Objective-C, like NS error, for example.
It's
Is
quite standard and it's
yeah.
disgusting.
Pointer. So there's that, and there's also optional tuples. You can make tuples optional. You can make the inside of them optional, or you can do both. So for example, you could say, let optional elements, and we'll make this a tuple where string, comma string, like that, equals Taylor nil. Optional tuples look like this. I put in here Taylor Swift. That's optional tuple. There's also optional both, for those who really love optionals. And the difference matters. This first one must return a tuple, but either element or both elements might be nil. This one will either return a whole full tuple with both names intact, or completely nil. And this one, what's it going to return? You're never going to find out. Could be nil, could be a tuple, could be names there, could be no names there. You're going to find out when you run the thing. So broadly speaking, I think optional elements are extremely common, optional tuples less so, and optional both only if your colleagues hate you. You can also compare tuples, as of Swift 2.2, I think, Swift 2.2. You can say something like this. Let Singer equals first Taylor, last Swift. Let Alien equals first Justin, last Bieber. And compare them. If Singer is Alien, then print match. Else, print no match. No match. That. So you can compare them directly up to what's called arity 6, which means tuples with 6 things inside. If you go beyond that, it can't handle it. I mean, it sounds silly. There is a code requirement. It's literally a lot of code in there to compare 1 to 1, 2 to 2, 3 to 3, 4 to 4. And they did some sums, and basically if they went any further, it started increasing the size of the standard library by about 15%. It got bigger and bigger and bigger just to add all these comparisons, which is a bit of a big thing. However, be careful comparing tuples, because if you had let Singer equals first Taylor Swift, then let Bird equals first Taylor, and then Breed Swift. If Singer is Bird, print match. Else, print no match. Lowercase m there annoys me. It prints out match. The two match. Because the labels are not taken into account when you do comparison, only the values. So be careful. You can also, and this is very common with tuples, for people who
Sorry. It also means that if you define first, so you have one
one tuple that's first and last, and then another tuple that's last and first, the labels will match, but they actually won't be equal because the...
Yeah, if you don't, I'm not talking about that particular problem. That's disgusting. But as a thought experiment, it'd be interesting to see what happens. Yeah, we're not talking about it. we're not talking about it. It's hideous. Thanks, Alan. What you'll commonly see are people who steadfastly refuse to go near structs. They want to hang on to their tuples as long as they can, is a type alias. You'll see something like this. Now, I am not a Taylor Swift expert. I can just use Wikipedia, okay? So I can say her father was called first Scott, last Swift, and her mother was called first Andrea, last Finley. Now, when they married, Andrea Finley became Andrea Swift, and we can write a simple function to represent that event. We could write func marry Taylor's parents. Now, brace yourself. You would write man. Well, that's tuple where first is a string and last is a string. Then woman, first is a string, last is a string, like that. And it returns a new tuple where husband is a tuple with first a string, last a string, and wife is first a string, last a string, like that. And inside, what we do is return man plus woman dot first and man dot last. Now, just for the sake of being fair, I should say this is precisely tailored to Taylor Swift parents. Marriage comes in all sorts of forms. It's a good thing. We like flexible things around here. San Francisco, right? So this is only for married Taylor's parents. I'm not making a statement here about marriage. So, this, as you can see, this looked all right. This looks like a nightmare come true. Don't write that kind of code. It's absolutely hideous. A better idea is to use type alias. You can say type alias, name equals first string, last string. And with that, you can replace most of this code. You can say here, man, name, woman, name, husband, name, wife, name. So it becomes significantly easier to read. Now, like I said, this is usually done by people who really are doing their best to avoid going to declare a struct for some obscure reason. There's a point where you are abusing tuples. It's not far off from that. I think that's the end of it. I think it is. I think we've gone through everything on the menu. It's only 5:30. Don't say you didn't get your money's worth, because you've got absolutely everything you've got to want to teach. So that's it. Thank you very much. You've been very helpful, very kind, and you've listened very carefully. I'd recommend, if you're able to, come tomorrow to the conference. There's some great speakers. I'm back again on Friday teaching Mac OS. If you are an iOS developer, you'll make a lot of money. Come back. It is so easy to make Mac OS apps. You'll be blown away. We'll make 2 complete apps in one day. You'll be like, oh, this is brilliant. There are tips galore for iOS developers. On Saturday, it's server-side Swift. How to make websites and web APIs and so forth using Swift. Become a full-stack developer in a day.